Hello, everyone. Uh, Thank you for joining our second part of the Privacy Preserving Machine Learning workshop. Uh, this workshop was partitioned in a morning session or a session that was destined for Europe and Asia, and then a second part of the workshop that starts now, which is more hopefully accommodating the time zones of Europe and the US and similar time zones. So our privacy preserving machine learning workshop is organized in conjunction with CCS this year. In general, the idea of our workshop is to present the latest research in the areas of privacy and machine learning. And we try to organize PPML, kind of taking turns with the machine learning conferences and security conferences. So this year, we have 7 organizers of PPML. We had 73 submissions to our workshop that were reviewed by 45 PC members, and we ended up accepting 41 of these papers. In general, we've been trying to be kind of open to have and present many new ideas. And out of these 41 accepted talks, 7 of them will be presented as presentations and talks, and the rest will be available in the poster session. Some more statistics include the fact that we were assigning 4 reviewers per paper, and they had about a month to review, and then we discussed all the reviews. And finally, the distinction between contributed talks and posters were made based on the recommendations of the reviewers, and also following some more discussion. We also, apart from the contributed talk, we have 4 invited talks. The first 2 of these talks were a few hours ago by Mireille Hidebrandt and Benny Pinkas. And now in the afternoon, we will have Ilya Mironov and Alexandra Korolova. As I mentioned, we were trying to accommodate as best as possible the many, many time zones from which our participants are coming. And that's why maybe you would not be able to view everything, all the talks today, but they will be also available on our website from recordings. Some logistics. So the talks and the presentation will be on Zoom here on this link. You can ask your questions either on the Zoom chat or the Slack channel that is provided by CCS. So you can find the links for both of them when you log in into your CCS account and click on the PPML workshop. The poster session will be hosted in GatherTown. Here, the link for GatherTown is also in the CCS website. We will post it also on the Slack channel and here on the chat in Zoom. And the password for the GatherTown is PPML21. The poster session will be at the end of after all of our presentations, and you will have reminders of how to log in to GatherTown. So these are our sponsors that we want to thank, the Alan Turing Institute and Google. And we want to thank again all the authors, the reviewers, the invited speakers, the contributed talks and posters, and the CCS organization team. And at this point, I would like to introduce our first invited speaker for the second part of our session. And this is Ilya Mironov, who is a research scientist at, I guess, currently Meta Platforms, formerly known as Facebook AI. Ilya received his PhD from Stanford, and since then has been experiencing industrial research in many settings, including a long work in Microsoft research, where he has done some foundational work on differential privacy, and later at Google, and currently at Meta. And today he will give us some Shakespearean inspiration through his talk that we are looking forward to. So Ilya, take it away. I will stop sharing so that you can present your slides.
Thank you so much for the introduction. Can you see and hear me well?
Yes, we can see your slides. Yeah.
Yes. So indeed, when I started putting together the slides, the name of my employer was different, but please take a look at the new logo. I'll give you a brief, a few minutes introduction into federated learning. We'll talk about synchronous and asynchronous federated learning, and I'll end up with a challenge to the crypto community, to the MPC community, of adapting their protocols to the realities, to the needs of the machine learning applications. So in a nutshell, federated learning is a setting for machine learning where data is kept locally and the model is updated through repeat interactions with the clients. A canonical example for federated learning is training a predictive keyword, which I try to illustrate on the slide with my subtle attempt at neuro-linguistic programming. So in this talk, our focus is going to be on cross-device federated learning, where clients are numerous, resource constrained, and intermittently connected. In other words, many, puny, and flaky. Very simplistically, the server broadcasts the model to devices. The devices update, compute local updates given their local data, and share those updates with the server. The process repeats. As stated, the setup doesn't really solve the problem that is designed to solve, which is privacy. Remember that let's face it, it is much easier to train a model if data is centrally collected. We don't do that because we want to keep data on devices. But the individual updates, and the emphasis is on the individual, can be just as sensitive as the raw data. A recent paper from Europe 2020 makes this point very clearly. This is, like, on the left is the ground truth, on the right is a reconstruction of the image obtained from individual federated learning updates. A remedy for this problem is pretty natural. Instead of the server observing the individual updates, we'll introduce a aggregation layer that will pass to the server the sum total of the updates from the clients. And this talk is going to be focused on this aggregation layer. Mathematically, this layer is super simple. It's a summation of multidimensional vectors shared by the clients. If we want to add, in addition to protecting the raw inputs, we also want to protect their outputs from inference attacks. And for that, we want to add differential private noise. Although in much of the talk, I won't explicitly be talking about differential private noise. In considering solutions for this aggregation layer, it's very natural, and indeed that was approach was proposed very early on, to consider a custom MPC protocol. And that kind of protocol is almost as it was proposed almost simultaneously with this basic approach to federated learning. Let's consider the constraints that this protocol must satisfy. One, machine learning likes to deal in floating point numbers. MPC assumes integers. Fortunately, this problem can be solved with gradient quantization, basically on the machine learning side. So we can adapt our training procedures to only outputting integers. Second, clients are mobile devices. Realistically, they can communicate only through the server. Peer-to-peer communications between thousands of or millions of mobile devices is not realistic. As I said earlier, clients are flaky. They can and do drop out midway through the protocol. And that leads us to the first protocol, which I'm going to sketch, called that goes back to Bonovitz et al. From 2017. In this protocol, and it's just kind of a very simplified version of the protocol, clients through the server share masks with all of their peers. Then they upload to the server their updates plus the sum of the masks that they sent out to other clients. Then the server can recover the sum of the updates if the masks are anti-symmetric, which is relatively easy to satisfy. There are clever tricks and ideas in this protocol to minimize the amount of communication, and also to deal with the dropping out clients, which I'm not going to cover. The computational overhead of this protocol is roughly the following. N is the number of clients, and in typical applications that I have in mind, it ranges between high hundreds and low thousands. Think about it like 500 to 5,000. And the number of parameters, the dimensionality of the vectors that the clients exchange can range from 10,000 to say 1 million. So the user computation is n public operations, n squared finite field operations, and d times n symmetric operations. On the server, the dominant factor is d times n squared symmetric operations. In a recent work by Bell, Bonovitz, Gascon, Lupon, and Mariana, the protocol is improved by nearly a n over log n factor, which is very substantial in our case, by changing the communication graph from a fully connected graph to what's called a hierarchy graph, where each client sends its masks to roughly log n neighbors to its left and log n neighbors to its right. And you can derive security properties of this protocol from the properties of the hierarchy graph. So far, so good. We kind of took care of this constraints. Integers, mobile devices that have to communicate through the server, the high dropout rate. But we also have to remember that in machine learning, the basic training operation is inherently iterative. The key to extracting maximal performance out of your setup is minimizing latency of each update. And the Bonovitz et al. Protocol is highly synchronous. The way it works is that kind of this is the arrow of time. We start with the model of the server. There are clients. The client download the model. we do the local updates, and launch the aggregation protocol, where all of these clients participate with their updates. So as described, this entire procedure moves at the speed of the slowest client. And let me tell you, clients in the real world are highly heterogeneous. So this is a graph of the client execution time obtained by my colleagues on a fleet of millions of real-world devices. And it doesn't look so bad unless you realize that the x-axis, which is the timeline, is in logarithmic scale. So the range, like so this is, I didn't say that, it's the probability distribution between the client's running time. So in practical terms, there is a giant difference between mean client execution time and the mean round duration if we look at the 99th percentile. A very natural approach to dealing with stragglers is to introduce some cutoffs. For example, we can use timeouts, or in the proposal by Google, what we do is over provisioning. If we are targeting, say, 1,000 clients per round, we'll be launching a computation with 1,300 clients, and saying that we are done when 1,000 clients responded. So in this way, the computation done by this slow clients, by the stragglers, is going to be lost. So even if it shows up seconds after the aggregation protocol starts, too bad. It has to its contribution will be lost forever. But clients are not just annoyingly heterogeneous. They're actually different in wonderful, interesting ways. And I'm saying it with full confidence in mind. I have data to prove it. So consider this example, again, taken from a paper by my colleagues, where we the model, this basic FL that just waits, I think, for nearly all clients, basically proceeds at the speed of the slowest client. It takes roughly 5 days to train, and contrasted with the federated learning with cutoffs, where the time to train is less than a day. The average perplexity, which is the score where the lower is better, it roughly think of this number as the model error. So the lower the error, the better. The perplexity of those models is in the same ballpark. They can do pretty well, are converge to comparable numbers. Perplexity measured on the clients with top 25% of data, meaning by volume, the clients with the top 25% of individual samples, is the same between is roughly the same between basic FL compared to the average perplexity. There's a slight drop, and the same with FL with cutoffs. But if you look at the richest client, at the top 1%, the clients with most data to contribute, then perplexity measured on those clients is significantly lower. It's a very meaningful improvement for basic FL, and it doesn't barely changes. It doesn't really change with FL with cutoffs. The remedy for a solution to the problem of stragglers is introducing asynchrony. And the asynchronous FL protocol called FedBuff has been proposed by, again, by my colleagues from Meta AI. And it proceeds roughly as it proceeds as follows. We set a target. On this picture is going to be 3 clients. Once 3 clients share their updates, we integrate them into the model. We update the model. But if a straggler, in this case, client number 2, shares its update, it will be merged together with updates from a new cohort of clients, right? So this way, like, we change the update protocol to accept late contributions. So this is kind of an insight that comes from that book, that late updates are still valuable, but really kind of we want to give high weight to updates to the most recent model. So kind of you want to kind of downweight them appropriately. But doing that is kind of non-trivial if you're operating under the standard, like if you want to apply the MPC protocol, the MPC aggregation protocol. So to implement the FedBuff, the asynchronous FL protocol, we propose using a trusted execution environment, TE, specifically for this purpose. So I'm sure that all cryptographers in the audience are familiar with TEs. If you come from machine learning background, then kind of I summarize it in a nutshell. And again, it's a highly simplified, very abstract model, like mental model. So it's a secure area within the main processor, which guarantees confidentiality and integrity against the host operating system. So kind of the bumper sticker version of T promise is what happens in T stays in T. And of course, with my cryptographer's hat on, it compels you to make very strong assumptions about your security threat model. The T is supported by in all the major vendors of processors, Intel, ARM, AMD. For RISC-V, as usual, there is like multiple proposals to choose from. And this is the effect that using the FedBuff protocol together with T has on the same model that I talked about earlier. So in the time that it takes, okay. Yes, so there's, there's a reminder to everyone that you can ask questions from me in the chat. I'll be glad to kind of attend them after, like, at the end of the talk. The FedBuff thus improves on the quality of the model for the average client, but significantly, it keeps improving if we measure its performance on the top contributing clients, right? And as I said, the difference between 57 and 39 is pretty giant in this world of language models. We can use the T functionality to add differential private noise, which is, by the way, can be integrated rather simply in the MPC protocol. Significantly, we can add a stateful DP protocol for the regularized reader without changing the model significantly. So to summarize, we have a difficult choice between synchronous federated learning with executed over MPC with all the wonderful properties that MPC, like typical MPC technology has, versus the asynchronous FL that does really well on the functionality, on the training the models that we care about. But our current implementation assumes existence of this trusted hardware. Here, I want to give a shout out to a paper that appeared a month ago that bridges the gap between these two approaches. It's a secure aggregation for FedBuff, and this paper has several very exciting, very interesting ideas. I'm pretty excited about that. The important benefit of using ATE is that our aggregation protocol can be structured in a way that minimizes communication between the server and the TE, and achieved by which allows to place the TE in a third-party cloud. One way of achieving it is that the TE doesn't interact directly with the clients. It doesn't determine the connections. It doesn't run a mini web server inside the TE. That would be craziness. Instead, it does a very compact, very simple operation that is carefully chosen to fit inside the TE, and that's one of the nice properties of the protocol that that FedBuff supports. So finally, I want to conclude with a summary of Desiderata for MPC for the mobile age. So some of them you've seen. Clients are mobile, clients are flaky, computation is iterative, clients are diverse. We want to deal with clients that are like dropping out, coming in late. Basically, I call it like flash mob MPC. What I didn't have a chance to cover in this talk, but it's a very important consideration in privacy analysis, is client selection. It balances competing objectives of clients anonymity. We want to select a cohort of clients from millions and millions of available devices without ideally learning who the clients participating in a single round of the protocol are. On the other hand, it sometimes makes sense to carefully select client cohorts to optimize for machine learning performance. And finally, there is we have to be aware of possible attacks through the adversarial training data. And there's another aspect to this entire FL learning that cryptographers and security applied security folks should be mindful of. And also, not in this talk, an important feature of FL protocols is their ability to compress updates. So there's typically a significant asymmetry between download speed and upload speed, and the latency of the protocol depends primarily on the upload of the clients. And here we have a tension between this aggregation layer being simple and aggregation layer being clever, meaning being able to process compressed gradients uploaded by the clients. And with this, I want to conclude the prepared part of the talk. I want to leave us with the conclusions, with this list of desiderata and links to two recent papers that summarize what I had a chance to cover in this talk. With this, I conclude.
Great, thank you, Ilya. Maybe I was just thinking that maybe it's best if people who have the question kind of ask them themselves, so that they can also add any clarifications. So let's try this model, and if it fails, then I can read off the questions. But I think our first question is from Virendra. If you want to speak up and ask your question.
Hi, nice talk, Ilya. Thank you. So my question is about cross-silo settings. All of the limitations you brought up, right, for synchronous FL with MPC apply to the cross-device setting where you have potentially millions of devices that are trying to collaborate with each other. But the question is now, how many of these limitations apply to a cross-silo setting where you have a handful of users?
Yeah.
They're far more reliable and they are resource rich, so
yeah.
they can even use GPUs.
Yeah, absolutely, yes. So this talk is very much about cross-device FL. I probably should have put it in the title. So I believe that for cross-silo FL, the kind of the design space is very, very different. And yeah, so
would you say that the problem is solved in the cross-silo setting, more or less? That doesn't have to be an answer to the question.
Yeah, I don't have strong evidence to argue, but I'd say that it's at least the problem of of finding a if right aggregation layer. It's much less acute in the cross-silo setting.
Thank you.
Okay, great. I think the next question is from Peter.
Yes. So hi, Ilya, and thanks for the really nice talk. One thing that was not very clear to me is why you have such a strong stance that we either have to go with MPC and do synchronous, or choose to do asynchronous and go with TEEs. So let me try to explain what I'm saying. So whether to use asynchronous secure aggregation seems to be somewhat separable from the choice of doing asynchronous model training. For instance, you could design a cross-device federated learning system that does asynchronous training, but then after training completes on devices, you could do cohort formations in a synchronous fashion for MPC to do secure aggregation. And that would still give you all the benefits you want. So because you're training asynchronously, any device that finishes pings the server, joins a cohort. Once you have that cohort, you update the model. You're still doing things asynchronously while using MPC.
Yeah,
Is that something you like?
Yeah.
You don't think
so I wanted to be mildly controversial, and I sharpened the choice deliberately to generate exactly this kind of response. How about we do something else? Absolutely, please do that. And it's a challenge to the ML folks, to the FL community, to merge together the best ideas to in systems, in ML, in MPC, to proceed at the to meet the challenges that I listed, which I hope you agree with under the best security threat model, right? So as long as you can tolerate all this the weirdness of real world clients, then we can that we can talk. Yeah.
Thank you.
All right, let's go to the next question. Fatima?
Yes. Hi. Hi.
Yeah.
So thanks for the talk. My question is like mostly about the security side of TEs, because TEs are known to, like have side channels and they've been attacked by them. So like, would that raise a concern in this setup that you're proposing? Or is it like, is there some differences in the model?
Absolutely, that's a valid concern. What I want to say is that there's a lot of trust put or kind of onto the entity running the computation, right? So, for example, you can, when I say that we kind of run a cohort of 1,000 clients, of these 999 can be like all be like simulated phones running on my server, right? So you already kind of trust the entity, the company running the computation with a lot, and in a way that is like not easily auditable. So in that sense, I don't think that side channel attacks on TEs is the biggest threat in this security in this model. But of course, I'm not answering your question whether you should be concerned. Yes, you are. Let's use the better, like the strengthen the TEs. I proposed one methodology, which is running them in a third-party cloud. We can kind of talk about alternatives to that as well.
Okay, thank you. Thank you so much.
All right, the next question is from Hui.
Yeah, my question is, in the federated learning framework, when we use differential privacy to protect the data privacy, you how to do the trade-off between privacy protection and the model accuracy?
Yeah, so I think the answer is, I can give a generic answer and I can give an honest answer. The generic answer is that the trade-off is roughly the same as in the standard machine learning, right? You can run the same, like what's called DPHDD, a differential private HDD, and basically FL will be running roughly the same protocol, like roughly the same machine learning protocol. If we add differential privacy to it. But an honest answer would be that it makes the like integrating differential privacy somewhat more complex into FL because typically kind of, that's kind of technical, but typically when you introduce differential private noise, you want to lower the learning rate, increasing the running time.
Okay.
Right. And the number of iterations. And that's kind of FL doesn't like that. So that's it's something that we kind of are taking very seriously, integrating FL plus MDP, and we don't have like very good solutions to this to this challenge.
Okay, thank you.
Okay, I think Jonathan has a follow-up remark.
Hi, Ilya. Thanks for the talk. Yeah, I had a follow-up question on Fatma's question on side channels, because at some point you briefly touched on the TCB of the function you're running in the TE. Yep. I wasn't sure if you meant to lower it because of the hardware constraint of the TE or for reducing the TCB itself, because like we see a trend in like Intel and AMD are going for these larger like machine-wide TEs. So what's your thought on that?
The main constraint is our ability to examine and to keep the code stable. It's reducing the TCB for TCB's sake. We want it to be simple, like basically world readable and updated like as rarely as possible. And indeed, the physical constraints of the device of the TE can be an issue, but it has to do with the just that we have to do computations over relatively large volume of data. So it's not the code that is the kind of the main constraint, it's the data that it processes.
Okay, I think I don't see any other questions in the channels, but let me ask my question then. So are we gaining privacy guarantees with this model compared to something where you just ask the devices to ship all of their inputs to the, if you assume you have this like highly trusted, impermeable computation environment, then why not just ask the devices to send all of their inputs, and you'll save on communication. You don't have to send back the ML model back and forth, just like do everything in these TEs.
Yeah, absolutely. So that's a possibility. It increases significantly, inflates significantly the trusted code base, and it really depends on how kind of what part of the computation you actually put inside the TE. If you want to put the entire training, then I would strongly recommend against that. If you want to make the aggregation layer more sophisticated, then now we are talking like we can draw the line somewhere.
I guess my question is, how do we decide what should be the rules to decide where to draw the line? And I mean, in terms of privacy, let's go through the extremes. If one extreme is that TEs are compromisable and you can extract the data, then these gradient updates, I think from them, I'm not an expert, but from them you can more or less extract the original inputs. Like you're not getting much into privacy, and then you're saying that for aggregation, maybe TEs are okay, but if we go to full ML, they are no longer. And I feel like in terms of hardware, the TEs that are really based on hardware, they support very simple things, maybe even simpler than aggregation. And then once you get beyond that, it seems that any computation gets the similar kind of guarantees from the security analysis part of TEs? Or is there something that's kind of in between that we know that this is the boundary where things become significantly more complicated and less secure?
No, like I think the boundary is kind of the trusted code base, right? If you say that you want to put the entire PyTorch inside TE, I'll tell you that I'll forget about that. Like I don't trust that. If you say that your code is like a few hundred lines of C, then now we are talking, right? So it's the TCB, but then there's a separate question of trustworthiness of TEs. As I said, I believe that FL has more fundamental challenges in terms of its trust model, meaning that you have to basically trust the code that runs on your device.
Great. Thank you. I see one comment in the chat, but I'm not sure who is the person with the comment. So
no, it's the session chair.
Okay, that's okay. Oh, this is.
Yeah, that was my question. Sorry, I'm logged in with this session share account. So yeah, my question would be like, if TEs like at some point they could break, or we don't know, and it would probably be hard to replace them. So is there a way to design a protocol that allows us to use this TE and maybe have some speed up due to that, but that carefully degrades in some way, that if or when the TE breaks, we still have some kind of security that's meaningful? And I think this goes in a similar direction as Mariana. So That's why I wrote it in chat. But
no, excellent point. Like it's forward security for TEs. I kind of if you have any clever ideas, then my mission is accomplished. The purpose of this talk was not to tell you something, but to challenge you to think about new interesting problems.
One last question about the bias reduction. You showed the number on the top 1% clients in terms of data volume, but did you see a significant improvement for, I don't know, the bottom 1% in terms of volume, or the ones that are taking 10 or 100x time to finish training? Did you look at those? I mean, did this really improve things for slow clients?
So specifically for the slow clients, I don't have an answer, but it was a significant improvement on the average, right? And you cannot explain the just by Marcus inequality. You can't explain the average improvement by gains on the top 1%. Yeah, I can. I'm sure. Like, are we out of time? Just.
Yes, I think we're out of time. I think, but by
yes.
now we are also out of questions. So let's thank Ilya once again for the interesting and provoking talk. But do you have a last comment, Ilya?
No, I'll put the links to the archive version on the chat, so you can just open them.
Okay, great. Thank you very much. And we will move to some of the contributed talks next.